good afternoon, everybody. Hope you're all well. Joining us from your respective either offices, socially distancing, or from your respective homes. I'm currently sat in the training centre at the moment, a little bit quiet, as you can appreciate. We've got Stephen Hall in the next room again, distancing himself. It's been a little while since I've been on camera, to be honest with you. I had to find a shirt that fit me. But yeah, like I say, my name's Mike. I'm the MFG project manager for Quadra into Autodesk, and I'm also joined on the call by my good friend and colleague Stephen Hall, who's our CAM Applications Engineer. Are you online, Steve?
I certainly am. Good afternoon, everybody.
Fantastic. Good man yourself. Right. So, without further ado, we'll get into the nuts and bullets of it then, if we can. So, for those of you who don't know him, this is our resident expert, Mr. Stephen Hall. He is 20 years in the industry as a CNC programmer and machinist, mainly automotive and wall coverings industries. He's been responsible for programming, setting and operating 3-axis, 3+2, using Heidenheim controllers. All programming has been done manually, historically, time consuming. And then he was 8 years at T2000, Training 2000, near to us, teaching apprentices on CNC machining and programming. And then 2D and 3D CAD, how to create 2D drawings and use AutoCAD and 3D models, assemblies, drawings. Some on the call I've noticed will probably have actually been on one of Steve's training courses for Inventor or AutoCAD or Inventor CAM. He then branched out into Inventor CAM 3 years ago, and then we snapped him up about a year or so after that. So back in 2018, joined us teaching CAD CAM, also at support level as well on the CAM side as well. So if there's any queries or issues outside, he's got the experience and the expertise there to lend the teachings to real world scenarios. So all the better. We are all the better and richer for having Steve with us. So let's have a look at a quick agenda. Like I say, before the lockdown, Matt Hutch and I ran an informal webinar on 2 Men in a Vault, and it worked really well. It's just a bit loose in the agenda, so we decided to run a similar thing. We'll look at what is Inventor CAM, the latest positioning of the product, because it has gone through a couple of rebrands, so it might have confused people up until this point. I just want to clear that up. Key benefits associated with having an integrated CAD CAM, how you can access Inventor CAM specifically, and then that'll be my bit. And I'll shut up, and then I'll hand over to Steve. He'll do a show and tell with you all, and then we'll pick up on any Q&A at the end. He will have Inventor CAM running live as well in the background on his machine, so if there's anything that you want him to pick up on, as long as it's not sort of in-depth or really specific stuff, then I'm sure he'll be able to pull up the screen for you and address that. Okay, let's have a look here. This has come from basically a bit of a mind map poll from people who wanted to expand on the challenges that they're experiencing at the moment during COVID. The biggest ones were the ones that got the highest votes. One of the particular ones that we've picked up on is that blue one at the top there, which is integration. And that's really everything that Inventor CAM is all about. It used to be known as HSM Works, the technology at least anyway. And since then it's in a couple of rebrands, as you can see. This slide just helps to explain to you the differences in the names that you may have come across and what it is known as now. You access Inventor CAM through the full PDM collection, and it's installed as a module when you run the Inventor installers. So, but then it appears within the CAM interface, which I'll come to. HSM Works does still exist separately. That second one in from the left there with the H next to it. HSM Works, it exists separately and integrates still with other platforms like it used to, like SolidWorks, Inventor, for example. If you work in the cloud, you can access CAM tools within Fusion 360 as well. It's simply that the HSM technology is now owned by Autodesk, so they've developed the product so that it integrates seamlessly within their products, which makes sense. But I hope that just goes to give a little explanation on how that HSM Works logo migrated over time into what we're looking at today. I mentioned the collection just now. Most will be familiar with what it includes. However, just to spell it out, I decided to throw this diagram in to show all of the departments that it covers, from initial bidding through to post-sales and service. You can see the Inventor CAM there bridging the divide between design, engine, production. You can do everything with it really: design, simulate, analyze tolerances that you can see, nest CAM, layouts, you name it, clash detection, no problem. And then if you choose to let the system manage the data, at the bottom you can see that Vault Basic is thrown in there as well, just a maintain of the links and dependencies that are associated with complex part files, assembly files, presentation files, and so on. So that was the collection. Now, so let's get into it. Benefits of integrated CAM. I'll be as quick as I can on this, but there's a lot to cover off. The way in which you usually set up, if you have a machine shop with a design office attributed to it, is that you'll have two silos. On the one side, you'll have the design office, product designers, design engineers who create the CAD data. And then you've got the programmers and the machinists who generally, well, they throw designs back at the DO with a very polite message to say that they can't make that. Really sorry. Yeah, normally polite. Looking closer, before you get to that stage, at A to B, you go through several steps, several different softwares, and several people to get to the machine stage for one product. Sometimes the machinist is actually the one doing the modelling, of course, if you've got somebody that covers all bases. But the large number of software transition stages and the file type issues still remain. So what you would do is you would take that CAD data and you would export it into a transferable format, so STEP or IGES or something like that. And then you would over on the machining software, you would take that common file type and import it into your machining software, off and on the CNC machine. Then you need to define the job setup, as you can see, then the machine operation parameters, and then that generates the toolpath. After that, depending on the experience of the complexity of the thing, you might need to verify the toolpath. Once that's done, you then post out the G-code. So that's that top line there, boxed off. Those 8 steps they're the tradition, or the holy grail of a perfect run. Yeah, there's no such thing. Nothing's perfect every time, and in the real world we know that things change, and when you're in a position of making precision engineering parts, even the smallest details often mean a complete rehash. The second line there explains this. So with the traditional workflow, the change would be identified, and the DO, the design engineer, would then open up and revise the CAD file and make the changes. That's fine, but they then have to convert it and then re-export it in a common file format. Shop floor then has to re-import it again and view the new data. This is hoping that it doesn't get confused with the first or the second or the third of all the drafts prior to that. The operations then generate, they do the operations, they generate the toolpath, they then maybe have to re-verify the toolpath if it's a lot of complex changes, and then that spits out the revised G-code. But in Inventor CAM, we can eliminate more than half of these steps. All you've got to do is create the initial model data and then set up the machining software with the CAD program. So already those 2 stages at the top have been knocked off. But the real kicker then comes when updates and changes need to be made to the part. All you have to do is open the CAD file, make the changes within the CAD, and then hit refresh and regenerate your toolpath. It's all done in the same Inventor interface. And then once that's done, you just push it through verification within the environment again, and then G-code it out. So we can shorten the overall time through iterations and time to manufacture just by having the CAM integrated into the CAD. Autodesk's belief is that design and manufacturing should now be a seamless process, and they're absolutely right. So what's happened there is that, a couple of quick bullets on summary there. We've streamlined the workflow. Also, because you're not dealing with multiple softwares or file types, you end up with less files, less file types, and a simplified data structure. Because you're working in one platform, the only extra training that you would really need is how to use the CAM tab and how to import your own machines and tool libraries. You don't have to retrain or on a completely new interface or anything like that. from different developers, different icon sets, blah, blah, blah. The natural benefit of having an all-inclusive CAD-CAM platform as well means that you have a full set of CAD manipulation functions, surface modeling, parametrics, built in, all the modeling tools that are built prior to milling. So you can fill holes in pockets, you can create or update runoffs, you can add fixtures. I mean, don't get me wrong, little caveat, there are products out there that do have a basic CAD modeling environment built in, but the thing is, most people will agree on the call, it's far from comprehensive. Sometimes it's only surface modeling tools, it's not parametric. And again, it's a different file format. If you're a machinist, you'd have to get the design office to make tweaks to tooling fixtures and so on if they didn't know how to do it. And the last point there brings us on to AnyCAD. Inventor includes the AnyCAD technology, which they bought into about 5 years ago. And it gives users the ability to direct edit files from other CAD programs. And this is important. You don't necessarily have to edit or convert the data in. You just point Inventor to the file that's saved in whatever structure you have, whatever filing structure that you use, be that Vault, Windows Explorer, whatever. You just point the Inventor to it, and then you use Inventor to edit it within Inventor in its own non-native format. So it could be SolidWorks or Solid Edge or whatever, as you can see from that screen there. That's not an exhaustive list either. There are many others aside that it'll take in. Steve Hall can show you that drop-down list from when he goes, file open, from all those that it can take in. Some of the mainstream CAD packages will allow you to import files from other developers. The benefit of the AnyCAD, though, is not that it can import the file, okay? It's that you can simply link to it and maintain an association with the other guy's part file. So if you've got a Creo colleague in a different office or a supplier that uses Solid Edge, for example, and that guy changes their Solid Edge file, you can save over the top, hit refresh, and the associated model updates within Inventor. So you don't have to re-export and import. Then, linking to the CAM, I appreciate I'm talking about AnyCAD here, but this is important with the Inventor CAM. In the CAM tab, toolpath and the strategy associated to that newly refreshed part that you've just re-linked from an updated Solid Edge, SolidWorks part, whatever, that can then be updated, as I explained earlier. Just hit refresh and it'll regenerate the toolpaths. There you go. That's my bit. I've tried to be as quick as I can, so I'm sorry if you feel like I've waffled a bit there. But what I'm going to do now is shut up, and I'm going to hand over to Mr. Hall, who's going to come online and tell me when to change slides. And he'll talk over the top on the Inventor CAM features. So, Steve, over to you, good man.
Thank you very much, Mr. Hacking. And again, thank you for that slide of the photograph of the elf. Of all the epic photographs you could have chosen of me running down mountains, much appreciated. Yeah. Good afternoon, everyone. Right, so I'm just going to quickly go through a few bullet points about the various strategies that come with Inventor CAM, and then we'll just jump straight into the software itself, and we'll have a bit of a show and tell. So as you can see from the current slide, we can change from an integrated 2.5 axis or 2.5 axis up to 5 axis CAM, multi-axis operations, adaptive clearing. We'll be covering 2D adaptive and 3D adaptive, and we'll also take a look at turning and possibly mill turn as well. If you could jump to the next slide, please, Mike. Thank you. So I'm just going to briefly touch on these bullet points. As you can see from the capabilities list there, it's quite extensive. 2.5 axis, 3 axis, 3 plus 2 axis, which is where the table will cradle or rotate and then lock in situ, so it can be machined in one hit, as opposed to having to remove it from the vise or the fixture. 4th axis milling is where we would set a chuck, for example, or a 4th axis separate entity itself onto the machine. Multi-axis milling is where we talk about simultaneous 5-axis machining. And then we're also looking at turning. There's also capabilities for cutting, as in laser cutting, for example, and also for using a probe for setting datums on multiple parts using a probe. So as you can see, it's quite extensive. Okay, so 2.5 axis milling. If you're not 100% sure what that means, essentially then anything that can be machined using 2-axis moves comes under 2.5 axis milling. What we mean by that is, as you can see from the list, you've got 2D adaptive clearing, pocket, contour, and so on and so forth. What that means is that the machine will position itself in the X and Y coordinate. It will then feed down in the Z coordinate, and it will then move in a series of X and Y coordinates to produce contours and pockets and faces, so on and so forth. This can also entail bore milling, thread milling, drilling and tapping, and so on and so forth. 3-axis milling, again, quite an extensive list, and as you can see from that example, what we're doing now is we're stepping into the domain of using all 3 axes to create surfaces at once. So using the X, Y and the Z coordinates of the machine. Still a 3-axis machine. We can create some complex forms, all sorts of weird and wonderful shapes just by using those 3D strategies. And as you can see from the list, we've got lots of different options. It depends on the surface that you are machining, the gradients of angles and so on and so forth, upon which strategy you would choose. But yeah, that falls under 3-axis milling. 3 plus 2-axis milling, short and sweet. This is where you can set your tool orientation so that if your machine has got 3 plus 2 axis milling capabilities, you can rotate and cradle your actual machine and then lock it in situ. So you can then produce pockets and holes and slots and so on and so forth on side faces, be they on an angle or at 90 degrees. I'm seeing it quite a lot now of these machines being out there in industry where they're locking themselves in position and then attacking it from all different angles. 4th axis milling is a really handy feature where you can use, for example, a chuck, and you can rotate the chuck around. The cutter itself will stay in situ. It's the chuck that rotates, and you can use a feature called wrap toolpath in where you can, we'll demonstrate that later on, but a wrap toolpath will mean that it can follow the contours. As you can see, that it will follow the contours of that boss as it's producing those pockets. Multi-axis milling. This is where we're going to be using simultaneous 5-axis strategies, such as swarf milling, multi-axis contour and floor. The video there, it's showing the floor control, and that is where a ball nose cutter is following the path of the contour. And as you can see, it will be cutting at the side or the edge of the cutter. It's entirely up to you. You can set whatever angle you want, and the table will cradle and rotate as it's being machined. Turning. For those of you that are running lathes at your industry, you'll be pleased to see that turning isn't forgotten. For a while, it was quite limited. The profile roughing, as you can see there, didn't exist. You had to use a grooving tool to rough everything out, which wasn't ideal. But Autodesk listened to the feedback from customers, and last year they introduced profile roughing, which, as you can see, is extremely good strategy, very efficient in that you can rough out entire components in literally in just a couple of clicks. It's very impressive. So it's a good display of Autodesk actually listening to the customers there and enhancing the product when they see fit. Okay, so what we've got here is a component, relatively simple. If you look at it in that view, you can see it's kind of like what we call a dog bone type shape. Got a couple of buoys in, and it's got some chamfer details on there. If I just quickly drop over into the 3D model and the model environment that you were all no doubt familiar with, you can see that there's an extra tab just about halfway across there for CAM. If I open up the CAM tab, and if I go into my browser and activate that CAM browser there, you'll see that I've got now the option to create my setups and my toolpaths and so on and so forth. The beauty of this is that it's the panels, the way they are laid out, it's very similar to what you're already used to. So if you're an existing Inventor user, when you're working in 3D model, for example, you can see that the panels, the drop down, so on and so forth, are very similar when we actually activate the CAM tab. So it's familiarity, you know, it's not a whole new screen that you've got to memorize and visualize and learn. It's pretty much as it is with the 3D modeling side of things. Obviously, there's a few strategies and features and buttons that you need to learn how to use. But again, if you're already an existing Inventor user, you'll find this very easy just to cross over and transfer into. Okay. First and foremost, I'm just going to quickly show you the tool library settings. So what I've done is I've preset everything, working my way along. I'm going to explain about each different strategy. It's kind of like a Blue Peter. Here's one I've preferred earlier. But if I open up the tool library, this is quite an important aspect of Inventor CAM. You'll see that for this particular program, I've got numerous tools that have already been preset. What we've got down here are lots and lots of sample libraries. So for example, different types of holders, different types of cutters depending upon the material that you're machining, different types of cutters with respect to the shape and sizes and so on and so forth. For example, if I expand this little column here for different tools of type, you'll see that we've got flat mills, ball mills, tapered, so on and so forth, face mills, slot drills. Okay, these are all generic. If I specify a drill, I can then, up in the top, go through a search process and say I want to find a 10mm drill. It will find me a bank of 10mm drills. If I select one of those, I can right-click. I could actually edit that tool. So if that's not exactly what I've got in my workshop, if I've got one that's shorter or longer, if I open up the edit panel, you'll see now that we've got a few options we can make. We can change the lengths of the shoulders and the flute lengths, the body lengths, so on and so forth. We can change the units from millimeters to inches if that's what we'd like to do. In the general tab, we've got the tool number, any length offsets. We can have a break control. So if your milling machine has a presetter in there which inspects the tool before and after any tool changes, you can activate that. If you don't have a tool changer, you can activate a manual tool change. Coolant strategies, just about every single option you've got there, flood, mist, so on and so forth. So there's a lot to choose from. You can even choose your the material of the cutter, high-speed steel, carbide, so on and so forth. You can specify what holder it's held in. You can create new holder geometry if you've got your own bespoke one. And most importantly, feeds and speeds. You can set the feeds and speeds. If you've got a certain drill and you've got a recommended speed and feed that comes from the manufacturer, or if the guys on the machines tell you that it runs better at such a speed and feed, you can override these yourselves. You can then create your own custom library in that respect. Okay, just going to cancel that for now. So first and foremost, we've got the component. First of all, we need to tell the software what setup we're going to use. And by setup, what I mean is I'm going to go up to this panel and select this icon here. So if I just double click there, the one I've done earlier, as you can see, it will immediately put some form of block around the component, what it second guesses as you think what the stock is going to be. Okay. This tab is the first tab that always comes along, be it in turning, be it in milling, be it in cutting, so on and so forth. Okay. You can nominate the machine. You can nominate the operation type. So for example, milling. You can set the orientation. Okay. By orientation, what I mean by that is I could select the Z-axis and the X-axis. So if that had been drawn by a designer who decided that actually he was going to draw it with Y pointing upwards, because there's no guarantee that the guy who designed the part would automatically have Z sitting as you would like it in the machine. You can just select the Z-axis and planes like so. So if I select Z-axis there, I can then set something what I want to be the Z-axis. Okay, I can click on the top face. I could click on a line on the component. It doesn't really matter. That is now set. The same goes for X-axis. Okay, what we can also do is if there isn't anything on the part that would help us to set the axis, you can actually go back into the modeling environment and you could create a sketched entity or a work plane or an axis or something, and then use that actual geometry to set your setups. Now that's the beauty of integrated CAM. If you're using a standalone, then you wouldn't have the ability just to drop straight back into the modeling environment and create something that would assist you. The next tab along is our stock tab. And again, you've got a few options. It will give us a second guess as to what it thinks is beneficial, but we've got a little drop down there. You can have a fixed size box. You can have a relative size box. By relative size box, we mean that maybe we want to add a millimeter all around, but there's no guarantee that the material we'll get off the shelf would fit that. So we use fixed size box, and we just put some coordinates in there, which best suits the material that we've got on the shelf. If I do a side view, you can see that we've got material there on the bottom, and what we've got there is the height of the stock itself is 30 millimeters, and what we've said is position the model offset from the top. It will default to center like so. And you see you've got an equal amount of material at the top and the bottom. Okay, we need as much material as we can at the bottom because we're going to grip that in a vise. So if I set it model position wise offset from the top, and then an offset of 1 millimeter is fine. You can see that I've got a millimeter of material to be machined off the top. I've got a nice healthy lump there to get a hold of using my vise. The next tab is the post-process tab. Essentially, you're just giving it a program name or a number. You can put some comments in there for the start of the program. And then you've also got machine WCS, which is your machine workpiece coordinate system. If you use FANUC, for example, then you'll understand that G54 is the datum of your machine. Okay, that's X, Y, and Z positions. Setting to 0 or 1 will automatically use G54. If you have multiple components on your machine table, so let's say you've got 3 components on there, then all you do is you tick the multiple offsets box, and you can give it some number of instances. So for example, we've got 3 there. We've now got 3 components. We'll increase each increment by 1, so it'd be G54, G55, G56, and so on. And then what you could do is you could then output the program to suit 3 components as opposed to 1. Okay. Operation order, you can preserve the order so it will machine one of them before jumping to the next, or you can have it ordered by tool, for example, whereas you could use a face mill to do all 3 components before tool changing for the next tool. Okay, so I'm just going to deselect and cancel that because I've already got one set up. Right, let's go back to the home tab. Okay, first option there, as you can see, we've got a phase 1 operation. That falls under this category, 2D milling. We've got 2D milling, we've got 3D milling. 2D milling is contour driven, 3D milling is surface driven. As you can see by this, 2D milling is perfect for this component because we've got a lot of contours with no surfaces, with no fancy shapes that we need to produce on there. So if I go up to this icon face, this would open up this panel. And first and foremost, it's selected the 50mm face. I just click tool. I can do a search through my existing library, or I can preset a series of tools within this component. Select 50mm face, and that's it. What you'll see is every time you start a feature on 2D milling or 3D milling, doesn't really matter, whatever the feature, be it 2D contour, be it parallel, be it 2D adaptive, you'll always see these tabs: tool, geometry, heights, passes, linking. Every single feature has those tabs. So again, it's familiarity. No matter what what profiling strategies you use, what 3D strategies you use, you'll always end up with those tabs. So you'll soon begin to understand that working from left to right will achieve the results. What I'm a big fan of with these strategies is just making the minimal amount of changes and then clicking OK. The reason being, it might work right first time. If it does, it's fantastic. If it doesn't get the achieved results, you can then go back in and start making some changes. If you open it up and then start making lots and lots of changes and then click OK and it doesn't quite work as you'd expected it to, you've then got to start firefighting and start investigating of all the changes that you've made. So minimal amount of changes. So I've picked a tool. The tool is defaulted to flood for that tool, which I'm happy with. The default speeds and feeds I'm happy with. So I'm going to move to the next tab, which is geometry. It will look at my stock. So I want to face mill all the way along the top of this component. So looking down from above, you can see that the stock is encompassed by that yellow line. So I don't need to make any changes to that. If I move to the heights tab, you'll see that if I look on the side view, you've got color coordinated heights. You've got clearance height, retract, feed, top and bottom. Okay. Again, every feature that you use has got those colors, color coordination there. And then I'm going to leave that exactly as is. I'm going to make no changes to that. For passes, I'm going to make no changes again. And the same goes for linking. I'm just going to click OK. So all I've done basically is select one tool. Okay, you can see now the toolpath has been highlighted on the component. You can see there the red arrow. If you see the yellow line, that's rapid. If you see green, that's what's called linking. So it's a lead in, it's linking in. Blue is where it's feeding across. As you can see, it feeds across. It then leads around there and comes off and up. If I give a quick demonstration running simulate, and I'll discuss the simulation environment later. As you can see, if I press play, it's pretty much done what I wanted it to do. Now, if I look at that from a side view, you can see that all of the cutter hasn't come off there. Okay. Now, the reason being is that the software is such that it expects the machine that you're using to be perfectly brand new and not have been on the shop floor for the past 25 years and had numerous bumps and bangs and your tooling and whatever to be perfect. That's not always the case. If that need be, and you need to sort that it comes off the machine, off the table, sorry. If I just right click and edit to go back into that feature, if I open up the passes tab there, you can see there we've got an option to pass extension. If I just put a figure in there such as 30 millimeters and press enter, if I now give an example, can you see now it comes all the way off in both respects. Okay, so it doesn't produce anything called a back cut. So you probably get a better surface finisher on your older types of machines. And that's it, face milling, very minimal. No changes, about one change made, but everything else straight out of the box. We're now going to move on to 2D adaptive. And again, this falls under the 2D adaptive environment. And if I quickly give a demo of that, what we've done this time is geometry. We've selected those outer edges. And all I've done is I've clicked on those edges for pocket selections. So I've told it that that geometry is what I want to rough out. 2D adaptive will do the rest for me. Heights, I've not changed anything apart from made sure that the model bottom has been selected there and the stock top. Passes, I'm going to leave it exactly as it is out the box. And you can see you've got an optimal load on your machine and your cutter there of 8 millimeters. And we've got some stock to leave. I've changed it so the radial stock to leave will leave 0.5 millimeters around all these faces. And then actual stock to leave, I don't want to leave any on the bottom. And you'll see also in the heights that at the model bottom, I've just told it to go 1/4 millimeter down. So if I just quickly zoom in on that there, you can see it's just slightly lower there so that we just cut a little bit deeper than we'd like. If I just click OK for this one, and again, I will give a quick simulation of that. The beauty of the 2D adaptive is that it will try and maintain the same amount of cutter load on the machine at all times. It won't be any abrupt or nasty changes where it will dig into the component and the cutter will start screaming and vibrating. It'll do its utmost every time to maintain that same load on the cutter. There's no nasty surprises. Okay. 2D adaptive roughing strategy. What we want to do now is we want to create a finishing strategy that machines around this profile. Okay. And we're going to use something called 2D contour. But rather than start the contouring operation from scratch, if I go into 2D adaptive and I right click on there, about halfway down I've got an option there, create a derived operation. If I say I want to use 2D contour derived from that 2D adaptive operation, it will then create a 2D contour operation and the same tool will be selected. If you wish to change the tool, then you can just go back into tool and change it as such. But the geometry has already been selected because it's derived from the roughing operation. We've already got that selected. The heights are all the same. We can make some changes if need be, so on and so forth. So we've got very minimal changes. And as you can see there from that one, actually machining around the component as a finishing up. Okay, drilling operation, very simplistic. We've got 2 holes there. We're not sure what size they are. Let's quickly go up to the inspect environment. Let's just measure that one. You can see we've got a 15mm hole there, and we've got a 20mm hole there. Nice and straightforward. We just go 2D operation in the drilling environment, and slightly different, not as many tabs for this one. We pick the drill that we wish to use. We decide what type of coolant we want. We've got it disabled for this one. Geometry, this is a good feature. You select the hole. If you have multiple holes that are the same diameter, you don't have to go through the arduous process of selecting each individual hole the same size. You've got a little button there for select same diameter. Okay? Heights. It will err on the side of caution. And if I spin it around and look at it from there, you'll see that the hole feature is there. The drill will not bottom out unless you tell it to. You may want that to be a blind hole. If that isn't the case, you just select that button there to put the drill tip through the bottom. And as you can see now, we've gone through the bottom of the component. And then lastly, drill cycle. What type of cycle do we want? Lots to choose from there. Do we want chip breaking? Do we want deep drilling? Do we just want to go through in one hit? If we do, we just click OK. And you can see there, the drill operation. We've got the other process there exactly the same. We could right click on that one and we could duplicate and then just change by selecting the new hole as opposed to the old one. Nearly at the end now, we've got a boring operation. This is a good feature. This will use something like a slot drill or an end mill. And if I just demonstrate for those of you that aren't aware what a boring operation is, if I just turn the stock off, what a boring operation will do is it will feed itself down into a hole and then spiral around in increments of 1mm. This one is defaulted at, just to bore out the hole to give us a superior finish and better size. And again, it's using both the holes. As you can see, that is just one operation for both holes. All we did for that one is in geometry, we just selected both of the hole features. What Inventor will do, it will recognize they are both different sizes and it will adjust itself accordingly to create each hole there. Passes is where you change the pitch. 1mm increments is what it defaults at. You can change that to as fine or as rough as you wish. If it's a finishing operation, you probably want to reduce that, but obviously it's a little bit more time consuming. The linking tab, leads in, lead out, you can make some changes. Again, I find that working straight out the box and just clicking OK gives you the best option. If you're not happy with it, you can then go back and tweak it yourself. Now finally, 2D contour. We've got there some chamfers. If I double click 2D contour, but this time for geometry, as you can see when I zoom in, I've selected the bottom of the chamfers there. As soon as I do that, if I go into my tool and I select a chamfer tool, the strategy will recognize that I'm creating a chamfer based on the fact of my tool selection. So that when I go into passes, you can see now a new box would appear. This isn't normally in our 2D contour, but as soon as you select a 45-degree cutter or a chamfer tool, it recognizes and it will adjust itself accordingly so that you can make some changes. Maybe you want to tip offset so it just drops down a little bit further, and we'll put around there like so. Okay, so I do appreciate that I've rattled through that one, but we have got quite a bit to cover. So we've gone from a basic setup, the face milling operation, 2D adaptive, 2D contour, 2 drilling operations, a boring operation, and a 2D contour. So now let's open up the simulation environment. Let's have a quick look at that. Okay, let's just rewind back to the beginning. So what you've got is just like a standard video play. You've got a play bar, you've got fast forward. You can jump forward through each feature strategy. And you can rewind back to the beginning. Okay. You've got an option there to show your tool. If you don't want the tool on display, you can turn it off. Same goes for shafts and holders. Toolpath, you can have it show them the entire toolpath or just a tail. I prefer tail because you'll end up with spaghetti all over your component. You'll see the toolpaths here, there and everywhere. What the tail will do is it will follow the cutter for a short while and then it will remove itself. And then finally, you've got the option for stock. Okay, the coloration, I prefer to use operation because it will differentiate between each operation. It will change the color. If you use material, then it will stay and maintain the same color. So you can't really see much of what's going on. So I prefer personally to use operation. If I press play now, you'll see it in its entirety. The model still exists underneath the stock. If you want to turn the model off, you can do. But as you can see now, we've got a roughing strategy there for the 2D adaptive. Once that's finished, it will then jump straight to the 2D contour operation, where we have a finishing cutter there. We're now drilling the holes, boring out, and then we're going to chamfer. You'll also see on this panel, you've got an information tab, giving you all the positions, be they X, Y, and Z, spindle speed, and so on. It'll also give you a time for each operation. And then you've also got a statistics panel there, giving you the total machining time, number of tool changes, and so on. As you can see now, we've chamfered out there. Happy days. Okay, so we've looked at that, we've verified it, we're happy. Okay, what we can now do is we can post-process. Okay, I can right click on there and select post-process, or I can go to the post-process panel up there. Either way, once we post-process, this panel appears. Now, Inventor has got a lot of different post-processors, as you can see from this extensive list. Okay, I've defaulted to Siemens Numeric. We've got to 840D. Okay, and you've got an output folder. Be that a folder on your machine, or maybe a USB drive, or maybe something on your network. You can give it your program name or number. You can put a comment in there if you wish to do so. You've also got a few modifications you can make to the post. These are editable modifications or properties that you can define for your post. So for example, some machines don't like the preload tool operation, whereas it will call up a tool, for example, tool 1, and then the next line will say T2, where it gets the magazine ready. Some machines don't like that. If yours doesn't like that, quickly tick that box there, click no, and then we're good to go. Everything else, we're going to leave it as is. I'm just going to click post, save it there. It's going to tell me I've got one there because I've always used the same program number. And as you can see now, we have the full program there. As you can see, it's got the program number. It's an MPF file because that's the Numeric one. Tools 1 to 6 and then 19 with the tapered. You can redefine your tool names if you need to do so. And as you can see, each individual operation is now highlighted there. T1, D1, M6 to change tool, spindle start M3, and those, as we said before about the workpiece coordinate, there's your G54. That's setting your data. And then we've got all the X and Y coordinates. What I do like about this is every rapid move is highlighted red, so you can quickly scan through everything. And if there's anything in there that you don't like and it's in red, you know that you can change it. Anything in green is where it feeds down, and then blue is where it will reduce contours. That's basically it. Straightforward and simple. I'm going to quickly show you 3D adaptive now. So what we talked about here with 2D adaptive, we did the 2D adaptive roughing strategy. You can now move over to something called 3D adaptive. The difference between the two is 2D adaptive is contour driven, whereas 3D adaptive is surface driven. So if I expand and open up this part, as you can see, if I rotate that, you can see we've got a component there where the form is out of the ordinary. It's not a standard 2.5 axis part. Okay, using a 3-axis machine, that can easily be achieved. If I open up the 3D adaptive control panel, you'll see now those tabs are identical, the 2D adaptive one as the geometry one, and so on and so forth. Like I said earlier, it always stays the same. We've got a cutter there, we selected. Geometry, we're just going to use stock geometry again. So basically everything inside there is fair game. We'll machine it away. Heights, exactly the same as earlier. If I look at it from the side view, we've got some clearance heights, we've got the bottom height, the top height, so on and so forth. And then for passes, we're going to leave everything as is. We can set a maximum roughing step down. If we want it to go deeper, we can do. Stop to leave again, but everything else we're just going to leave. I'm going to click OK. And then if I quickly let this generate, you can see the toolpath there is a bit more extensive. If I just right click and simulate this toolpath, you can see that it will do its utmost to maintain the same amount of load on the cutter as much as it can at all times. Again, no aggressive moves, no sharp moves into corners and full diameter cutters where the machine starts screaming. And if I just speed that up a little bit, I'm conscious of time. You can see that it's gone to the bottom, it's roughed out its initial step, and now it's working its way back up, taking smaller cuts to produce said form. So again, very minimal clicks, complex part roughed out in no time whatsoever. Very, very simple. If I close that one, we're going to have a look at some 3D strategies now. I've got another operation there where I've used 2D contour, where I've just cleaned up the edges, just like the last program where I machined around. What we're going to look at now is the parallel and floor. 3D milling has a lot of strategies depending upon the gradient. So for example, you've got 3D contour. What I really do like are these little tool tips. If you hover over one for long enough, it will tell you what each individual strategy does. So for example, contour is for steep walls. Okay, and parallel is probably one of the oldest. It's been around for years, but it's very, very useful. And what that means is that if I quickly give you an explanation, what we're going to use is a ball nose cutter. So something with a decent radius on. Okay. The geometry, same again. We're just going to keep it as the silhouette. So we're not going to make any changes. Tool center on boundary, which means that it can pass over the edges. If you have it within the boundary, then you'd have some little scallop marks there. But again, it defaults to tool center on boundary anyway. Heights, we're going to leave as is. Passes, the only thing we change is a step over. I think it defaults to something like 10%. So I've just reduced the amount of step over to 0.5 millimeter for this one. And then I'm just going to click OK. And as you can see, looking from above, you can see why it's called parallel. Got lots and lots of nice, neat parallel lines there. If I go back to home, if I just show you from this view, what you'll also see is though, the more aggressive the drop, the 0.5 mil increments will maintain the same. Therefore, we could end up with some scallops. Okay, that's why sometimes it's best to blend two strategies together or using the one that's relatively new called floor. But for now, let's just leave that one as is. If I quickly simulate that one, I'll turn the stock off and you can see what's going on. If I there you go. If I go from that view there, you can see that we're moving in X, Y, and Z to create that, that form on top of there. So again, minimal amount of button clicks gives us a very good form on top of there. What you can also do is, if you're not happy with the direction it's going in, maybe your surface finish, you want it to be a different gradient, for example. If I go on to edit there, go on to passes, I can change the pass direction. So I could go on 90 degrees, for example. And then, okay, and that one will generate me a toolpath there, which you can see now it goes off in a different direction. Okay. Now, one of the new kids on the block is called floor. Okay, and again, that falls under 3D milling. It's a 3D milling and it's also a multi-axis milling strategy. And floor is essentially very similar to parallel. The geometry, you just click the face and you choose a direction, be it in X or in Y. Okay. Passes, you don't actually give it passes, you don't nominate sizes, you actually give it a number of stepovers. And by achieving that, what you will get is, if I look at it from above, can you see at the top, we've got some relatively short gaps. We've got some slightly bigger ones, but if you look at the actual cutter path, you can see we've got straight parallel lines down there, but along here, it fans out, so it follows the contours of the component. Okay, so that might be preferable depending upon your surface finish. Again, you could go to the nth degree for this one, give yourself a really fine surface finish. You could put 100 in there and you get a very good finish on top of that component there. Again, very simplistic. What I'm going to do is I'm just going to change this one back so that you're not sat around watching it all day. What I'm going to do is I'm going to change multi-axis. Okay, so rather than being a 3-axis machine now, let's assume that we jumped onto a 5-axis machine. We can activate multi-axis, and then let's say we want to put a tilt on there, because they always say you should never machine on the edge of a right on the bottom of a ball nose cut. You should try and machine on the edges to get a better finish. So if I put a 15 degrees sideways tilt in there, okay, and then actually let's change it so it's, no, let's see what happens with that one. And then simulate that one there. If I look at it from the edge now you can see it's using the full simultaneous 5-axis capabilities of the machine, like so. Okay. So again, if you see some 5-axis machines producing components like this, you instantly assume that it's quite technical and there's a lot of work goes on in the background. There isn't. It's quite simple as that. Inventor CAM will do all the hard work for you. You just nominate the face, the number of step overs, give it some limitations, then it's not trying to spin itself around here, there and everywhere. So like I said, just put a 15 degree sideways tilt, and as you can see there, it's doing all the hard work itself. And if you remember looking at the machine, that spindle will maintain vertically. It's the table that will be rotating around there. Okay. So those are your 3D adaptive strategies. Conscious of time, I've waffled on way too much, so I'm just going to go into 3+2. If you have a 5-axis machine that doesn't do simultaneous machining, but you want to tilt your component over without removing it from the vise, if your table has got a cradle or a rotation or any axis of rotation in there, very, very simplistic. If I go into the setup part, what I've done is I've created a datum in the center there. Okay. What I've done for the model is I've just used from solid as opposed to a generic stock, just to save a bit of time so we're not having to rough everything out. Okay. And all I've done is I've gone on to a standard 2D pocket cycle. So I've just used 2D pocket there. I've picked a tool, but with geometry, I've got a little option there for tool orientation. If I just deselect that one and I deselect that, we've now got a tool. We now need to tell it what orientation we're going to be working in. If I expand this tool orientation panel, first of all, I need to select a Z-axis. So I'm just going to pick that face there as a Z-axis. I'll just deselect that one. That's now my Z-axis. X-axis, I can then just pick an edge. Excuse me, like so. And then as you can see now, if you look at my triad for my X, Y, and Z, they've now positioned themselves there. If I wanted to maintain the same datum at the center, then I could do, or I could change the point of my datum by going to selected point. Let's say I want my datum to be over there this time. It really is that simple. Okay, and then I just pick the pocket that I want to machine. The heights, we'll keep that one as is. If I say bottom height, top height, so on and so forth, if I say selection this time for bottom height, and I pick that one, you can see there we've got a cutting strategy now. So in the machine, the table would have rotated itself in that orientation, so that when we come to simulate that one now, you can see that it would pocket it out like so. So again, it might look complex when you see it on the machine. If you walk past the machine and you can see the machine as the table tilted up and you're creating a pocket like that one, it isn't. It really isn't. The CAM package will do all the hard work for you. It's just a case of knowing what it is that you need to do. And that's just simply set a tool orientation, pick yourself a cutter, select the pocket, and let the CAM package do all the work for you. Okay. So turning, we'll have a quick look at turning. For the turners, all you turners out there. As I said earlier, this used to be quite limited. You had the turning option there. You didn't have profile roughing, profile finishing. You just had a profile operation. And all the roughing out strategies were done with their grooving tool. It was quite long-winded and not the greatest. As I said, Autodesk listened to the feedback from customers, and feedback was that they needed a roughing operation. And so last year it was introduced into Inventor, and yeah, it's much, much better. The setup tab for this one, slightly different. Again, it's the same 3 tabs that you're used to, but this time we've changed the operation type from milling to mill turn. The moment you do that, when you go into stock, it will default to a fixed size cylinder. Okay. If you're happy with the initial setup, then you can just select OK and leave it as is. But what you can do is you can pick your Z-axis, and it will default to the center of the component more often than not. What I also like is you've got an option there, chuck reference, and that's that green square there. That will denote where your chuck is. You can tell it in relation to your stock where the chuck is, so that when you run a simulation, if you're going to strike into that chuck, you'll get an error message. You'll get a big red flag saying that you're going to have a bump. Okay, very important. What I also like is this option here, spun profile. If your component has a few holes in there, or maybe a couple of flats or a hexagon feature on there, if you leave that unchecked, then Inventor will try its damnedest to machine everything that it can see on that component. So you could end up with some errors. So what they've introduced is something called spun profile. So it will eliminate any features that aren't part of the turning strategies. Stock, we'll leave it as is, as a fixed size cylinder, and same again for post-process, but you can see, just like every other strategy, it's the same tabs. Facing operation, very simplistic. If I double click, you can see that in our tool library, we've got numerous turning tools. Okay, and again, you've got the option to create your own, or you've got the option to use what's default from the current library that they've got. If I go into sample tools there, you can see that different types of holders, sorry, different types of turning tools, different tips. Okay, if it isn't what you've got, then you could create your own turning tool there by going into the insert tab, changing what type of insert it is, all the different shapes that are known to man. As you turners will know out there, there's a tip for just about every occasion, all the different types, the different gradients. So you can create your own tool library if you have your own tooling like so. Geometry, it's defaulted to the entire component. Okay, the front we've defaulted as a model front. We're going to leave everything as is with that one. The radii is the same as the heights for the milling tab. Okay, you're just giving it your clearance and your outer tab, so on and so forth. Okay, so again, we're going to leave that one as is. Passes is same again. If you want it to be roughing out with multiple passes as opposed to one, you just check the multiple passes box there, tell it that we want to step over 1 millimeter, and that's pretty much it. I don't think there's anything. There's one thing I did want to show you. Yeah, that's okay. If I just open up the profile roughing, what I quickly want to show you for this roughing operation for there, we'll leave that one as is. We'll put allow grooving there. I'm just going to quickly go to that roughing up. I'm going to click OK. And by and large, that roughing cycle looks pretty impressive. Okay, it's taking 1 mil cuts. Everything looks absolutely fine. And you'd run that, you know, as is. However, if you zoom in on that little groove there, can you see that the software, it assumes that the cutter you've got can do this. It will try and dig in. It'll try and rough out as much as it can there. I'm fully aware that there are a lot of tips out there that won't be able to maintain that, or it'll just end up chipping. If that is the case, then all you need to do, you go back into edit, and then under your passes, you've got a grooving option there. Change that to don't allow any grooving. Click OK. As you can see then, nice straightforward strategy, cutting straight through there. Go back to home for that one, and then we'll simulate that. We'll turn the stock on. So we will face, rewind there, and then we'll see the roughing operation. Okay, I'll just speed that up again. And as you can see, if you've already run this simulation, but you want to see the finishing strategy, then all you need to do is little fast forward button there, jump to the next operation, and it will jump to the 2D the contouring operation. As you can see there, got the finishing up into like so. And all I did with that was go onto there, right click, same as before, create a derived operation, and say that I want to use a profile finishing. By doing that, I don't have to select anything else. Only thing I did change was the cutter, like so. Very, very straightforward. Yeah. Fully aware that the time is getting 3:10. So just before I hand back over to Mike, what we often get asked is about when post-processing. We often get asked what posts are available. Okay, you get some generic default ones that come with the software itself, and as you can see, there's a lot to choose from. If your machine isn't on that list, then don't despair. There is a link at the bottom of said panel. If I open up that, hopefully you'll be able to see the same screen. If you have, for example, a Haas or a Herco machine, if you just start typing Herco in there, you can see it will default.
Steve, just a quick one, chat.
Yes.
We're still seeing Inventor, mate.
Aha, thank you. New share. There we go.
Spot on.
Thank you, Mike. Just undo that. So that website, that link will take you to this website. It says Fusion 360. Ignore that. It works for Inventor CAM as well. They both share the same CAM library. So if you've got a machine in there that you're looking for, let's say we're looking for a Herco, you can see that you've got posts available for your machine. Always worthwhile keep an eye on these because there may be some updates. For example, you've got a little recent changes operation there. You see that anything that's been reported back to them, they will then update accordingly. That doesn't just apply to milling machines. If I go into the drop down, you can see that we've got milling, turning, so on and so forth. So if we go to turning, you'll see that we've got quite an extensive list, which is getting added to quite a rapid rate. They've got lots and lots of different machine types getting added to. As you can see, some of them quite recent, 30 days ago. So at some point, something's been reported and something's been updated. Right, apologies for waffling on, Mike.
Hey, you're all right, chap. Nobody's left. Put it that way. You've definitely had everybody's attention, pal.
They probably fallen asleep. I shall stop that share. Right, thanks for listening, folks. And any questions?
Stay online, though, Steve. Yeah.
Yeah, absolutely, absolutely. And
we can. Well, I think everybody online will agree with me. I can tell that you're a trainer. That was really good. That. Well, you're definitely not a blooming timekeeper as well.
Well, this is true. Yeah.
Could have said it's an hour and 45, shouldn't I?
I'll go back to the Inventors screen, and that way, if there's any questions that we can answer here and now, maybe I could give a demo if we have any questions.
No, fair shout. Take control in a sec. I'm just going to quickly just say thanks for that. That's fine. It was all good, short, sweet, and concise. I'm going to pull this up right now. The slide just before Steve jumps on. Obviously, don't take the salesman's word for it. We've implemented Inventor CAM in a few companies now. This is the last slide, by the way, before we jump on to some Q&A. I've got a couple of questions in, Steve, so I'll be ready. We've implemented Inventor CAM in a few companies now. Steve has trained, one of which very local to us in Clayton, is a company called All Speeds, make subsea cutters amongst other very heavy engineering products. Brilliant success story for Inventor CAM. Their MD is now signing off on very complex geometries because the DO is simulating the G-code out to him so that he can see the output within the Inventor CAM. So worth mentioning as well, there's a mixed bag there. There was a mixed bag of expertise. I'm sure Steve will agree with this too. Expertise and age demographics, you know, a couple of guys there, very experienced, skilled machinists, knew what they did it very well, didn't really want to change, didn't see the benefit. But tell you what, Steve will attest, after training, we went back to Rory, had a quick chat with him on Wednesday to make sure we could use this slide. And he said they're converted, they love it better than what they did before. And they've also said, if anybody online wants to get in touch with us, I can make the introduction for you and put you in touch with Rory, and he'll happily have a chat with you about what it's like being used on the coalface and what it does for him. So really, really good from Rory, that, and I'm very grateful to him. We've had a couple of questions in actually, Steve. I mentioned before about the list of file types. Can you just take control and just show that list of file types off?
Fantastic. Yeah, as Mike mentioned earlier, it's quite simply a case of going to the File, Open tab, and you've got files of type. It will default to Inventor files, as you would expect, but the little drop down there, you can see that we've got numerous parts. We can go for a standard step file, which is generic to most pieces of software, but you can also see that we've got files from other manufacturers such as CATIA. We've got Siemens NX files, Pro Engineer, so on and so forth. So SolidWorks files as well. So quite a very quite an extensive list and a strong selling point in terms of receiving models from customers who may not use the same software.
Just appreciating time, Steve, just quickly. I've got somebody on quite early on asked, will the simulation highlight any collisions?
Yes, good question. Yes, it will. If I simulate that toolpath, you'll see at the bottom, we'll see the green line, okay? As Shrek says, it's good to be green. If I quickly change, let me think, yeah, that'll work. If I quickly change that cutter to be ridiculously short, let's say it's going to be 10 millimeters sticking out. When I click OK for that one and select, okay, when I simulate that now, can you see those little red lines there? So they're your visual representation. That will tell you that you're going to get a bump or a bang. If you hover over it, it will tell you what the issue is going to be. But I do appreciate that sometimes you might scan over that and you might miss it. You've also got an option there to stop on collision, so that as soon as you press play like so, you can see it's lit up red, it stops, it's going to make a bang, it's going to smash into the top of there. So you can then investigate what's gone wrong and sort it out.
Cool. Cheers for that. Our company often uses specialist tooling. How would this be replicated using CAM?
Specialist tooling?
Yeah.
Right. Again, very simple. If I go to the tool library, that's probably the best way about doing it, and I've got an option there for a new mill tool. Okay. If I expand that, and we've got different types of cutters there, so you can create your own tool there. If it is a ball mill or so on and so forth, you can put all that information in. If you've got something that's a little bit out of the ordinary, you've got an option down there, form mill. Okay, if I select form mill, then what you can do is import file. When all you need to do is go into the Inventor modeling environment and just model up your cutter. So let's say you've got some weird and wonderful shape on there, be some rads or angles or whatever. Just draw that up yourself, model it up, and then just sketch and revolve. You don't need to worry about the holder, just the actual cutter itself, sketch and revolve, and then you just import file on that button there, and that will give you your own specific tooling. Yeah, very, very simple again. Okay, but again, one that's people aren't aware of. They just assume that everything's just straight out of the box, but as we all know, machining isn't like that. There you go.
Cool. Looks like somebody's been stalking you, mate, prior to this. I've seen your blog demonstrating templates.
The templates blog.
Yeah.
Right. Yeah. Again, something handy that doesn't really jump out at this one until you're aware of it. So what you get more often than not is you get a lot of components that will use the same strategies. So, for example, you might use face mill and 2D adaptive and contour. And you might use all of those strategies, but on different components of various shapes and sizes. And it can be a bit of a long-winded process, having to go through the process over and over again for different components. What you can do is you can, once you've created that those strategies, if you select the top one and the bottom one, and what you can do is you can right-click and you can store them as a template. You've got an option there. Okay. When you store it as a template, you then give it a name, so on and so forth. Then if I just delete all those, what you can then do is create initial setup on your new component, right click there, and you've got an option there, create from template. And all of those previously saved templates you've got there will appear. Okay, so as you can see there, one that I did on a demonstration a while ago was a face with 2D adaptive pocket. So that's very similar, you know, so that might be something we might need. You can do it so it creates all templates, or you can just pick specific ones. But if I just create all templates there, you see that now it's created lots of different templates that I need. You can see the little red X just tells me that some information is missing. I just then double click, click a new tool, the geometry I'm happy with, click OK, and presto, done. It makes life a lot easier. Yeah, it's a nice little feature, is that one.
It takes a lot of the pain out of it, really, I suppose, doesn't it?
Absolutely. Yeah, it really does.
Make this in and just tweak it to suit.
Yeah.
That's class. Question. Oh, right. So you're the trainer. You know what you're doing. It's a quick forward question here. How long is training?
The training course we offer is 2 days. That covers basic 2D machining, 3D machining, and turning. I do appreciate that some companies might look at different strategies and so on, so we could create bespoke training to suit their needs, but more often than not, the 2-day course does get people off the ground and get them up and running. And
what do we do specifically with Allspeed? Can you remember?
What we tend to find with Allspeed is they have the 2-day course, but they sent the guys, actually the machine operators, on the course, as well as the guys in the programming office, so that the lads on the machine had an understanding of what was going on, that they weren't in fear, because we get that with a lot of machinists where they think the skills being taken away from them. So what Rory actually did is he sent all the lads on the machines on the actual course, and they've all got a workstation or a laptop alongside the machine, and they're actually writing their own programs whilst the machine is running, because they're enjoying the tinkering side of things. I've been on site to a couple of courses quite a few months ago now, where they didn't have any lathes, so they just wanted some extra milling strategies. So we jumped into a bit more of the 3D machining environment. We could spend a bit more time. So we are fluid. We can adapt to whatever the requirements are.
Brilliant. Right. Okay. That is, at the moment, I'm not seeing anything else coming on from anybody. So I think we've answered everybody's questions that need it. What I'm going to quickly do, guys, is I'm going to put Steve and my contact details at the end. This is the last slide. When I click share, there you go. Right, he's immortalized in an email address. So there's no narrative for this slide, really. This is the end. I'm really grateful to Steve for coming on and supporting us with this, particularly doing the live screen share stuff. It was really, really valuable, mate. We've covered off Inventor, we've covered off the AnyCAD technology, which means you could bring non-native stuff that isn't made by Autodesk. It could be SolidWorks, Creo, Pro-E, whatever. Bring it into Inventor, and then you can use that to feed off to actually do your strategies, develop your posts, and then change it as the model part changes, even from different CAD platform providers. So I hope it's been informative for everybody. If you've got any feedback for us, good or bad, don't care, let us know. It's all valuable. And again, we want to hear from you on if you've got any product ideas, areas that you want us to cover in webinars such as this. Okay, it's informal. It goes through the various stages. It's succinct enough. You know, I appreciate it wasn't 45 minutes long. It was an hour and 25. That's my bad. Mine's probably going to waffle at the beginning. But yeah, everybody that's on right now, thank you very much. A virtual round of applause for Mr. Stephen Hall there. I hope I didn't waffle too much before he came on and did the good stuff. So, like I say, email addresses are on the screen, mike.hacking@quadrasol.co.uk or stephen.hall. Don't forget it's with a PH, stephen.hall@quadrasol.co.uk. Email us. If you want to speak to Rory, email me, let me know, I'll put you in touch. But for now, I just want to say thanks again, and I'll take your questions and feedback and speak to you all soon. Thank you very much indeed.
Thanks very much, guys. Take care.